8.2, measure of running time. We did a little bit discussion on this topic before. In this video, we will understand in much more details. All right. Let's look at the general analysis of algorithm. So when we do that, what is the analysis of algorithms? What do we need to do when we do analysis on algorithms? We need to do a lot of things here. So after we get a solution of a computing problem, we need to estimate amount of resources that we used. What's the meaning of the resources, right? It's pretty vague. Resources. What kind of resources? Here, we typically talk about two different types of resources. The first one, you know it, the running time. That's the primary resource. That's the most important resource. Running time, execution time. But there is another important resource. So we call a secondary resource. That's the memory space used by your algorithm. Usually, you may not be able to, aware of it. Get aware of it. You may not realize the existence of that secondary resource, but actually, it is important because it can affect the running time. In other words, if your algorithm does not use memory space efficiently, so waste a lot of memory space, okay? So when you run your program for some time, so the memory space run out quickly, so then your program running slower and slower. Now, especially, we know a computer may run many programs simultaneously, right? So the memory space, that resource is very important. When the memory resource consumed quickly, then the operating system need to manage, swap in, swap out, right? Some swapping pages. Remember, hard drive, memory, pages, swap in, swap out. That will be very slow. That kind of operations usually very slow. So in general, your algorithm will run very slow. So we want to avoid that kind of situation. All right. Now, method used to study analysis. Two methods. All right. The first one, theoretical. So we do mathematical analysis. So that's the theoretical. Another one, empirical. Empirical, write a program to do experiments. Our project one, actually, you need to do empirical analysis. Okay? So you implement 3 different algorithms evaluating polynomials, and then you compare their execution time, that kind of thing, empirical analysis. Okay? All right. Next, efficiency of algorithms. The first one, time efficiency. For the running time, how efficient you use the running time. Time efficiency. Sometimes people call time complexity. Also, similarly, space efficiency. or space complexity. Okay, yeah. Here, yeah. Regarding the space efficiency, so we want to look at that, with more precise understanding. Yeah. Here, yeah. The amount of memory units required by the algorithm in addition to the space needed for its input-output. So what's that? So here, because for the data, in order to process the data, you need memory space to store the data for input and output all the time, right? No exception, all the time. Yeah. So that's common for all the problems, right? For all the problems, you need memory space to store data for input and output. So for that common part, we do not need to look at it. Okay? Yeah. So we only look at the part in addition to memory space for input and output. Because other than memory space for input output, you need more memory space, right? Because you need to manipulate your data items, copy here, there. So sometimes you may need a lot of extra memory space. Yeah. So that's why that part is the main consideration when we look at this space efficiency. Yeah. So that's the first point. Second, we have a concept we call it in-place algorithms. In place, yeah. We saw it in the previous video, but that concept is different. We put one element in place, right? So that concept, in place concept there, so you put in the right position when the array is sorted. So that's that in place. But here, this in place algorithm, associated with algorithm, the meaning is different. The meaning is the extra amount of space used in your algorithm is bounded by a constant number. If your algorithm has this property, we call your algorithm in place. You have an in place algorithm. So you have this special meaning. So when we talk about in place algorithms, you should use this definition, in place. Okay? Yeah. So you can think about the selection sort we just did. Do you think it's in place or not? Because that rely on finding the minimum, that problem. When we work on the minimum problem, is that in place algorithm? Yes. Yes. Yeah. Because the extra space you used, constant. One location. Yeah. When you swap two elements, you use one extra location. So that's why it's in place. Yeah. Then your selection sort is also in place because you're repeatedly using that in place finding minimum solution. Yeah. So also in place. Yeah. All right. So next, another concept. Input size, the data input, there is a data size. What's the meaning of the input size? Yeah. Here, I give you two cases. Yeah. The first one, number of data items in the input. N, given array with n elements, number of elements in the array, that's the input size, right? Yeah. So that's the commonly used case for the input size. But there is another one. It's different, but sometimes you have that situation. The second one, the magnitude of number n. The magnitude, how large is that number, the magnitude, could be treated as the input size. Why? In this situation, only one number. The data is given just one number. So that number could be large, could be small. The magnitude of that number, we treat it as the input size. Why? There is one famous problem follows this situation. Checking primarily, prime, you know prime, right? Prime numbers, prime number. Check if a given number is a prime or not. So checking primality of a positive integer n. Given a big positive integer, can you determine if that one is a prime or not? The larger the number, the harder, right? If it's, it's not an even number. If it's an even number, it's easy, right? It's even number, it's easy. But it's an odd number, non-trivial odd number, because if it's a multiple of 5, it's also easy, right? Some non-trivial odd numbers, now it is extremely hard. How hard it is. So here, let me describe a little bit how hard it is. You can use a very powerful computer, supercomputer even, to try to check primality of a 1,000-digit number, 1,000-digit non-trivial odd number, 1,000 digits. Can you imagine that? Several thousand digits that you check primality. Using even supercomputer, you need many years, many years to get an answer. Is that hard? Many years. So that's the reason the modern encryption, the internet encryption algorithm is built on top of that primality of large positive integers. Large positive integers. The encryption method built on that. Because it's very hard to break it. Very hard to break it. All right. So that's the input size. All right. So we know the larger the size, the harder the problem. Usually. So here I say usually, most of the time, but not 100% of the time. There are some problems, even the input size is relatively small, the problem is still extremely hard to solve. Okay? You may have that kind of special problems sometimes. So that's why we say usually. All right. Next, measure running time. To measure running time, we have some basic knowledge already. So let's continue from there. So we need a scientific method to measure the running time. And we want a stable measure. So remember we talked about this before, stable measure. So what do you mean stable measure? It does not rely on the hardware computers. Very fast computers, very slow computers, doesn't matter. So we don't want our measure relies on the performance of the computers. All right. It does not rely on the quality of the programs. Another factor that can make running time slower or faster. Quality of the program, right? Yeah. But a good one, the good measure, should not rely on that. Okay, yeah. All right, so the main approach, so we used, yeah. We did a few examples, but here we try to, summarize the theory a little bit. Yeah. The main approach use the basic operations. Basic operations. We count the number of basic operations. Yeah. So what do you mean? What's the meaning of the basic operations? Yeah. The operation contributing the most to the total running time. Yeah. All right. Yeah, that's the basic operation. Yeah. So then we count the number of basic operations used in the algorithm using counting techniques. Counting techniques. Yeah. So you need to count. Yeah. All right. Another thing, how do you identify basic operations? Right? Yeah. So we need to fix that problem. Identify the basic operation of an algorithm. So we use this criteria. Okay. Yeah. Usually, the most time-consuming operation in the algorithm's innermost loop. We know when we implement an algorithm, usually we need to use many for loops, while loops, right? The loops, yeah. Sometimes nested loops, right? Yeah. You may use nested loops. When you use nested loops, in the innermost loop, when you do some operation, because that's the most time-consuming, the innermost, you do that operation most of the time. Yeah. So we make that basic operation. Yeah. All right. So with this kind of description, then we look back our examples so we can quickly identify the basic operations. Yeah. In problem number 1, evaluate polynomial. Obviously, multiplication is the basic operation, not addition, right? Multiplication dominant. Takes most of the time, most time consuming in that problem. Okay? Problem number 3 and number 4, together similar, yeah, because we use comparison operation in these two problems. Yeah, so you can see that easily. Yeah. All right, so that's our video 8.2. Yeah.